Okay, so last time we talked about interference of wave, kind of wrapping up. So let me review a little bit. Okay, so last time we talked about interference of two waves coming from two different sources. For example, if we have two speakers, blue and red, and then let's say we are here, okay, and then the blue one give out wave, the red one also give out wave, and we call S1 to be source number 1, S2 to be source number 2, and where we are listening is called the point P or position P. The condition where you will hear, in the case of sound wave, to be loud or soft sound or quiet sound will be whether the two waves interfere constructively or destructively. Alright. And the condition for those two cases depends on what we call the path difference. Which we use PD as an abbreviation. And path difference, it's defined to be the difference in the distance from S1 to P and S2 to P. Okay, it's a distance. Again, it's not like vector subtraction, vector addition, or something like that. Okay, it's the distance, so you don't need to worry about the direction of the wave propagation. If this one is equal to a multiple of lambda, so n lambda, and again n is an integer, in this case also including 0, because they can have exactly the same path, so the path difference is going to be 0. This is when we have constructive interference. So you're gonna hear sound which is louder, okay, but if it's equal to half integer, so n plus 1/2 lambda, then the two waves gonna cancel each other out all the time. So this is what we call destructive interference. Okay, and anywhere in between you just have like not perfect addition, not perfect cancellation, right? So we are interested in this kind of extreme cases, so constructive and destructive interference. All right, and we're gonna be using this again when we talk about interference of light. Okay, so this is very important concept, because this gonna apply to any kind of wave we talk about, no matter how large or how small the wavelength gonna be. But later on, when we talk about light wave has a very distinct characteristic because of a very small wavelength. There'll be some additional approximation that we can do. So you're gonna have some more formula related to this interference that applies only for light wave. Okay, but until then, this is what we have, and this applies to any kind of wave that we study in this class at least. And then the other thing we talk about is standing wave. Standing wave is nothing but an interference of two waves, but in this case the two waves are not coming from two distinct sources. It's actually coming from just one source, but the wave traveling through the medium reaches the end, so the wave reflects back. So you have two waves originated from a single source. One is going to the right, that's what we call incident wave, and the other one reflected back, that's what we call reflected wave. And these two waves can interfere each other, and that's what we have, which is called standing wave. Okay, so in general, you're gonna have the wave added together. Remember, we use trigonometric identity to add the two waves together, and the two waves traveling in the opposite direction, so it's not an easy, cancellation or easy, like addition. So you need to use some formula to reach this expression, which is sine kx cosine omega t. Okay, so this is an expression for standing wave in general, and then we impose what we call boundary conditions, because we want to be a little bit less general. Okay, so this expression is in general, it means that it's gonna work like for any two wave which comes together, right? But in reality, you're gonna have to impose like the physical constraint of your system, right? And what we did in the last lecture is that our constraint is imposed in the form of n fixing. So what we mean is that we gonna fix the n. So it's gonna be a little bit strange, because like if you fix one n, how do you put in the wave? So let's not worry about that too much. Like you can hold, or kind of like try to disturb the wave, not right at the end, so a little bit close to the end, so you don't need to kind of like shake the end which is supposed to be fixed, right? So that's kind of like the detail we don't need to worry about, but we can be sure somehow to put in some wave even though the two ends are fixed. Okay, so in this case we're gonna have the boundary condition, so EC boundary condition, which says that, so the way we set up the coordinate, remember we call this x equal to 0 and x equal to L. So essentially L is the length of the string. Okay, so because both ends are fixed, then the displacement at both ends must be 0. So y of x equal to 0 and y of x equal to L at any time must be 0. This is our constraint. This is what we call boundary condition. Okay, two of them. One is this one, the other one is this one. Okay, and these conditions will allow us to write down the condition for possible value of k. Okay, not any k will work, only some value of k is gonna work and satisfy this boundary condition. And we found that condition by saying that sine of KL must be equal to 0. Okay, and this means that KL must be equal to integer times pi. Okay, that's a condition for zeros for sine function. So sine of 0 degrees, 180 degrees, 360 degrees, 540 degrees, right? So any multiple of pi gonna give you sine equal to 0. And in this case, we're gonna not include m equal to 0, because otherwise the whole wave function y will be 0, so that's kind of not what we want, right? So we're gonna start m from 1, 2, 3, 4, 5 like this. And remember what is k? K is 2 pi over lambda. So essentially this condition for k gives us condition for lambda. So that means lambda must be equal to 2L over m. So that means in order to have a nice standing wave in this system, which is one end fixed and the other one is also fixed, lambda, which is the wavelength of the wave, can be this value. Okay, it cannot be just some random value. If you put in wave which has so-called like wrong wavelength, that means wavelength that does not satisfy this condition, then you're not gonna have standing wave. You can have the wave inside the system, but the wave will bounce back and forth and interfere in a kind of random fashion. It's not gonna look as nice compared to when you choose like the correct wavelength, and that's when you have like a nice standing wave. Okay, so this is the condition to have a standing wave in the system. So we talk about the fundamental case. The fundamental case is when you have the longest possible value of lambda that fit in the system and give you standing wave. So fundamental case is when lambda is the largest. Well, how do we find that? Well, we just look at what's the possible value for m. So large value for lambda comes with small value of m, right? And the smallest value of m that we allow is m equal to 1. So lambda equal to 2L, and of course this is because m equal to 1. Okay, and suppose that we know the velocity of wave in this system, and in this case, which is a string fixed by 2n, the velocity of wave, remember, of the string depends on two things. One is the tension of the string, and the other one is the mass of the string, which we call mu here. And that's fixed by the system. Okay, so that's how you tighten the string, that's how you choose the string. So you cannot really change this unless you change the string type. So that's kind of fixed. Okay, so V is fixed, and lambda in this case is 2L. So we can use this formula, V equal to F times lambda. So the frequency we have in this case is V over lambda, and that's gonna be, well, I'm not gonna substitute this in because that's gonna make things too messy, but I gotta write lambda equal to 2L like this. This is called the fundamental case because this is the largest lambda possible and the lowest frequency possible, so that you have a standing wave in this system. Okay, and because of this, we sometimes call this F0 or sometimes we call it F1 because like next thing we have is F2, right? So it probably does not make sense to start from 0 and then go to 2 or something, but that doesn't matter. It's the lowest possible. Okay, it's the lowest possible value for frequency that we have here. Okay, so this is called the fundamental frequency of the system. Okay, and that's the lowest frequency we can fit in to get a standing wave. In terms of how the wave looks like, so this has to be shown clearly in the animation which we showed last time, so I'm not going to repeat that. But in terms of the kind of diagram, right, it looks like this, right? And it looks like this because it's kind of like just half of the sine wave and then oscillate up and down. Okay, remember the n, the 2n has to always be fixed. Okay, so it just oscillate up and down. Again, if you don't remember how it should look like, then take a look at the animation that I showed in the last lecture. Okay, so this is the fundamental case. The next wavelength that we can choose, so next one, is lambda equal to 2L over m, but now we choose m, which is the next value, so m equal to 2, so lambda equal to L. Frequency is V over lambda. V stay the same because that's fixed by how we set up the system. But now since lambda changes, the frequency must also change. So in this case, the frequency is V over L, and this is actually 2 times F0, so 2 times the fundamental frequency. because it's the value 2, so sometimes we write this f2, and it's twice the fundamental frequency, so this is sometimes called the second harmonic frequency, because it's twice the fundamental frequency. And you see why I said earlier that sometimes the fundamental frequency is written f1 instead of f0, because f1 is just 1 times fundamental frequency, which is the fundamental frequency itself. Okay, but actually it doesn't matter whether you call it f0 or f1. Okay, we know what it means. Okay, so in this case the wavelength is actually L. So if you draw the picture of the string in this case, right, is the whole wave gonna show up? So it's gonna look like this, right? So it's kind of like a full sine wave, and it's gonna oscillate up and down. Okay, this is the second harmonic frequency. And then for the next one we have the third harmonic, and you can kind of see the pattern already. So lambda is going to be 2L over 3, and F3 is going to be 3V over 2L, which is 3 times the fundamental frequency. Again, this is called the third harmonic frequency. And when you draw this, then it's going to be kind of 3 section, right? Because wavelength is getting shorter, so somehow you have to fit that in. Alright, something like this. And then you can just go on, like F4, F5, F6, so on and so forth. One trick that I'm gonna tell you, and it helps a lot when dealing with this, is that when you look at this diagram, you can somehow like see how many, what we call like the lobes. So this is one lobe, L-O-B-E, I think. Right, it's like one chunk, one loop of the wave. So in this case we have 3 of them, right? 1 here, 2 here, and then 3 here, right? So there are 3 lobes. So the rule here is that, so each lobe is gonna be lambda over 2. And we use this trick to figure out what is lambda. For example, in this case, the length of the string is L, that's fixed by our choice, right? So the length of the whole thing is L. So how many lobes we have in this case? We have 3 of them. So 3 lobes altogether give you the length of L. So that means 3 lobes equal to 3 lambda over 2 equal to the whole length, which is L. Okay? So that gives you lambda equal to 2L over 3, which is the same thing that we had earlier here. Okay, so this is kind of a little bit like more kind of like visual aid that you can use to figure out what is the wavelength of this particular harmonic frequency, right? So if you have kind of like, different condition, for example, you might have something like the 5th frequency or the 4th frequency, that you have something like this, and the standing wave looks like this. So how many lobes we have here? We have 4 of them, right? 1, 2, 3, 4, and the whole length is still L. So what is the wavelength? So the wavelength is, well, the number of lobes, which is 4. Well, each lobe is lambda over 2, and that's equal to L. So that means lambda is L over 2. Like this. Okay, so each lobe is lambda over 2. So this is an easy way of figuring out what should be the lambda. And this is going to be, again, useful in the next case, which I'm gonna talk to you about in a few moments. Okay, so remember this, that each lobe is lambda over 2. So half the lobe will be lambda over 4. Okay, and we're gonna see that in a few moments. Alright, so this gives you a series of harmonic frequency, which is always a multiple of the fundamental frequency, right? So this fact can be quite useful because, like, let's say we have a string, and then somehow the information that you got is the fifth harmonic of this system, this string, F5, is equal to, let's say, 1500 Hertz. This is given. Alright, this is given. What is the sixth harmonic frequency of this system? What is F6? Right. So very simple question that can be quite complicated if you go like the difficult way of calculating. But the fundamental frequency times the number of, you know, the number of harmonics gives you F5 or F6, right? So this one can be written in terms of fundamental frequency like 5 times F0, right? Because it's the fifth harmonic. So using this, you can see easily that F0 is probably 300 Hertz. Right, so this one gives you F0 equal to 300 Hertz. Now our task is to find F6. Well, F6 is just equal to 6 times F0. So that's going to be 1800 Hertz. That's it. Okay, pretty straightforward in this case. Alright, and we can do something more. So let's say this string has a length of 60 centimeters. So using this information, can we find out what is the wave velocity? Well, this is a little bit more involved, right? Because it seems like there's nothing, well, not enough information. Actually, it's enough, because let's choose F5. Oops, sorry. So F5 again is 1500 Hertz, and for F5, that means we have 5 lobes in the string, right? So it's gonna look something like this. Okay, 5 of them. It's supposed to be the same kind of shape, but and bad at drawing sine curve. So it looks like this. So this is the fifth harmonic, right? The fifth harmonic has 5 lobes, and 5 lobes means you have 5 times lambda over 2, because each lobe is lambda over 2, like each loop or each lobe or whatever you want to call it is lambda over 2. Okay, so in this case we have 5 lambda over 2 equal to the whole length, which is L, and we know L is 60 centimeters, so that's going to be 0.6 meters. Okay, so lambda is simply 2 over 5 times 0.6 meters, and that's gonna be 0.24 meters. That's the wavelength of this particular harmonic, fifth harmonic. Okay, so we know frequency, we know the wavelength, so we can calculate the velocity of the wave, v equal to f times lambda, and that's going to be 1500 times 0.24 equal to 360 meter per second. Okay, that's something that we have here. So this is the wave in the string, the speed of wave in the string. Try not to be confused with the sound wave velocity. Okay, they are two different things. This is the wave in the string, even though the number turns out to be kind of close to the sound wave in air. When you hear a guitar string, sound from a guitar string, like, well, a guitar is something that looks like this, right? Something like this, a guitar string, right? When you hear the sound from a guitar, there's wave in the string itself, which has nothing to do with sound wave in air, because it's the wave in the string. It's gonna have that wave even if you don't have sound wave produced. Okay, but that vibration of the string interact with the sound, with the air molecules around it, and that produce sound wave propagate from the guitar, and that's another wave. Okay, so there are two waves going on here, the one inside the string and the one coming out from the string through the air. Okay, so I just want to point out, because sometimes you're confused, like you get some number which is not this, and then you think that it has to be the velocity of sound in air, which is about 300, because we are used to hearing this, sound from the guitar string. They are two different things. Okay, so don't get confused with that. Okay, so this is the case where the two ends are fixed. You might ask, like, is there any other ways that we can fix the boundary? Well, the answer is yes, because you can have the string at the end to move kind of, well, not really freely, because we still need to keep it in place, but we can let it move up and down. And that's gonna be a little bit unusual, because that's what we see often. But you can do it this way. You can fix one end of the string, but the other end of the string, instead of fixing to another kind of like post or something, you can fix it onto, some kind of like a ring, a metal loop or something like that, which can slide up and down along, a post or something like this. So you're fixing it horizontally. It cannot move horizontally, but it can move up and down. So it's free to move up and down. Okay, it's free to move up and down. And this one is still fixed. And you can also have like both ends to be like this. So both ends are free to move up and down, but that's kind of a little bit hard to implement in real life. So so let's just talk about this case. This end is what we call free end. And the boundary condition will be different, because now this one is allowed to move up and down. So it's not fixed. Okay, so if we say like the whole thing like this is length of L, then you cannot write y of x equal to L at any time equal to 0. This does not work anymore. Okay, because it can move freely. So we have slightly different boundary condition. I'm not gonna go into details like what exactly the condition here, because we have to talk about like the second derivative or the first derivative or something like that, which is too mathematical involved, and we will instead try to figure out the possible wave that can fit in using just regular drawing. So how do we draw? The fundamental frequency, which is the longest wavelength that we can have in this system, gonna look like this. So this is the whole length of the string, and because this end is free, right, so we allow it to oscillate up and down like this. Okay, so it's gonna be something that looks like half the fundamental frequency that we had before, right? But only half of them. So this is how it looks like. So as time passes, then this will come down and then go down like this. So this end is always fixed still, but the other end is free to go up and down. Okay, so this is like how do we find the wavelength then? Well, remember that one lobe is lambda over 2, so this is half the lobe, right? Because one lobe is like the whole thing like this, and this is only half of them. So this whole thing, this is half a lobe. Half a lobe has the length of, well, each one is lambda over 2, so this one is 1/2 of lambda over 2, so that's going to be lambda over 4, right? So in this case, the longest wavelength that we have actually is going to be 4L, because lambda over 4, which is this, equal to L. So that means lambda is 4L, right? So the longest wavelength that you can fit in this system to get standing wave, right? So once we change the end condition here, somehow the wavelength is twice from what we had before. Okay, so in this case, the fundamental frequency f0 now is v over lambda is L, not L, v over 4L, which is different. Okay, the fundamental frequency is different from the case that we had before. So boundary conditions, meaning that how you fix the ends of the string, gonna give you different frequency, different fundamental frequency. And what about the next one? Well, the next one we have to draw another picture to fit this with smaller wavelength, right? So the length is the same, that's the length of the whole string, but now we have to fit in smaller wavelength with the condition at the end still the same. So it's gonna looks like this. Okay, so this end here is still fixed. This end here can still move up and down. Okay, this is the next one. Alright, this is the next one. And what's the wavelength? Well, we have how many lobes? We have one lobe here, and we have half the lobe here. Okay, so it's 1.5 lobe. So that means it's gonna be 3/2 of one lobe, which is lambda over 2. Lambda over 2 here. Okay, so 3/2 lobes. Each lobe is lambda over 2, and the whole thing is of length L. So this is L. So that means lambda is 4L over 3. The frequency is V over lambda, so that means the frequency is 3V over 4L. Okay, and you see something strange here. I'm gonna come back later. But now I'm gonna keep on going to the next one so that we can see the whole kind of pattern. So the next one is what we do is something like this. So I need to redraw this. So something like this. Okay, so this is the next one. This is fixed, this is free. And in this case we have 2 lobes and a half, right? So 2.5. That means we have 5/2 times lambda over 2 equal to L. So in this case lambda is 4L over 5. And the frequency is V over lambda, and it's gonna be V over 5. Sorry. 5V over 4L. So you can see something which is different and very, very different from what we had before. Remember what we had before is that The fundamental frequency is F0. So what do we have? And the next one is called the second harmonic, is twice the frequency, twice the fundamental frequency. And then F3, the third harmonic, is 3 times the fundamental frequency. That's what we had before. And what did we have before? The two ends are fixed. Now one of the ends is free. Only one is fixed. You can see that the next frequency, which is this one, that's not twice the fundamental frequency. It's actually 3 times. I shouldn't write F0 here because it's not. So sorry about that. It's gonna be 3 times F0. And the next one is 5 times F0, right? So the structure of harmonics is different. In this case, you don't have the even number of harmonics. So F0 is whatever the value that set by the system, okay? But the next one, the next standing wave you have is actually 3 times, not twice. And if it's 3 times F0, there's no reason to call this the second harmonic, because we want to keep the term harmonic to be like, okay, second harmonic is twice the fundamental frequency, third harmonic is 3 times the fundamental frequency. In this case, even though the next one happening here, we don't call it second, we call it third harmonic, because it's still 3 times F0. So next one will be fifth harmonic. Okay, so in this particular system, you don't have even harmonic frequency appearing in the system. So there's no F2, no F4, no F6, no F8, no F of even number. Okay, so sometimes you can describe this as only having odd, right? Odd number 1, 3, 5, 7, 9. Only having odd harmonic frequency. Which is different from what we had before. Before we have all possible harmonic frequency. Okay, so changing the end condition of the string changes the structure of this, right? So that means if you have the fundamental frequency in this case to be something like, you know, like 200 Hertz, the next frequency that can happen in terms of standing wave is 3 times this, so that's going to be 600 Hertz. And next going to be 5 times that, it's going to be 1000 Hertz. Okay, so it's very, very different structure from what we had in the other case. Okay, and last thing we're going to talk about this is we're going to kind of talk about exactly the same physics but different system. So we're going to talk about the sound wave in what we call the air column, and this is the basis of many wind instruments. Some of you might know how to play, some of you might have seen, like trumpet, trombone, flute, organ, right? So every instrument that involves wind blowing into a tube, that's going to be what we call the air column. An air column is essentially just a tube or a pipe. Like this. Okay, and so we can put in sound wave in this air column, very similar to the way we put in wave in a string like this. Okay, it's just different kind of wave, different kind of medium. Instead of string, now we have air, but the physics is the same. And the physics is the same in the sense that because the length of the tube is finite, finite means it's not infinitely long, okay, there has to be something happening at the end, right? And how do we describe that? Well, remember, sound wave can be described using the pressure wave. Okay, and for the tube, when you reach the end of the tube, okay, the air inside the tube get in contact with the air outside. And the air outside is what we say there's no pressure, or at least there's no gauge pressure. So the pressure has to be 0 at the end. That's the boundary condition that we have here for air column or for this tube. Okay, so visually it's a little bit different from what we had before for the string, because for the string it's kind of clear, right? If we fix, we see it fixed. If it's free, then we see it free. But in terms of the tube, it's something that you cannot see directly, but it's the same kind of boundary condition that we have. Okay, so I'm gonna write it down like this. Like at the end, we have P equal to 0. P here is the pressure. And the other end, P also have to be equal to 0. Again, this is because at the end of the tube, the air in the tube is in full contact with the air outside. So the pressure has to be equal to the pressure of the air outside, which we assume to be 0. Okay, and if you remember our first semester of physics, right, there's the term, I think, gauge pressure and absolute pressure, right? So the absolute pressure is obviously not 0, because otherwise we cannot live at the surface of the earth, right? So it's 1 atmosphere. So P0 here means it's P0 away from the atmospheric pressure. So it's the gauge pressure. Okay, so how much more, how much less compared to the atmospheric pressure. But any case, we're gonna call it P equal to 0. Okay, so if P equal to 0 on both ends, then in terms of physics, it's gonna be exactly the same as the case where the strings are fixed at the both ends. Fixed string, fixed end. This is also fixed end here. And they are exactly the same. So everything you have learned applies in the case of this particular tube where both ends are opened. So open end here. Okay, so this is where some of you might get confused. The end of the tube are opened. That means the pressure is 0, so it's equivalent to the two ends are fixed for the wave in the string. Okay, so think about what I just said and try to make sense of it. Anyway, what you learned from this applies directly to the case of the tube here. So that means for this particular case, lambda is gonna be 2L over M still, and the trick with the lobes still works. Like one lobe is lambda over 2, it still works fine here. Okay, everything else is the same. Okay, and we're gonna have like a sample calculation in a few moments, but you probably realize that there's another case where I should write it here. So lambda here is 2L over M. Well, I don't want to write it this way. I want to write it in this way. It's easier to see. So it's 2L, 2L, and then L, and then 2L over 3, 2L over 4, so on and so forth. Okay, so similar to what we had earlier. Yeah, another case you can have is when one end of the tube is actually closed and the other end is open, and you can probably guess that it's gonna be the same as the string where one end is fixed and the other end is open, like this. The other way around, right? Because something like this. So this is fixed, and this is free end like this. So why, if you close one end of the pipe, you can have kind of like similar to free end in terms of the pressure? Well, because it's inside the tube, it has no contact with the air outside, right? So the pressure can build up to be any value it wants. There's nothing from the outside that's trying to control it. Unlike when you have open end here, right, where the air is in contact with the air outside. So you don't have any choice but to have zero pressure here, right? But if this end is closed, you close out that kind of contact between air inside and air outside. So P here will not be zero, okay? And then P here will be zero still. So equivalent to the string, that means the left end is free, the right end is fixed. So we are back to the case that we just talked about up here, okay, where one end is free, the other end is fixed. And in this case, lambda is the same as before. So lambda is going to be 4L over 3, 4L over 5, 4L over 7, so on and so forth. Okay, but what I'm trying to say again is that if we talk about sound wave in air column, it's nothing new. Okay, everything you know from this can apply right away in solving this kind of problem. Okay, but you need to kind of choose the correct kind of connection between the two kind of physical system. And to demonstrate that, let's do a quick kind of example calculation for the air column. So let's say we have an air column, and let's say it's 1 meter long, 1 meter long like this. And because it's air and we talk about sound wave in air, so the velocity of sound wave in the air column is just the velocity of sound in air. And it depends on the temperature, whatever, but let's just say it's about 330 meters per second. This is sound velocity in air, which is what we have inside this tube. And let's say that first we open both ends. So both ends are open. Our task here is to write down the lowest 3 frequencies of standing wave that can have in this kind of air column. Okay, so the lowest 3 frequency of standing wave that we can have in this tube. Alright, so let's start with the lowest one. Well, it's the case where both ends are open, so it's similar to the case where the 2 ends of the string is fixed. So the lowest is when you have something like this situation, and I always like to draw it because it's gonna give me right away how I should think about in terms of the wavelength, right? So this is L, and lowest frequency means you only have one lobe or one loop of the wave. So lambda over 2, which is one lobe, we only have one, equal to L, so that's gonna be 1 meter. So lambda is 2 meters. Frequency is V over lambda, so it's 330 divided by 2. It's equal to 165 Hertz. And that's the fundamental frequency. That's the lowest frequency that we can have in this case where both ends are open. Okay, both ends of the tube are open is equivalent to both ends of the string fixed. Okay, that's the connection. And what's the next one? The next one is the second harmonic, because we know that this is the case where you have all possible harmonics, right? You don't skip the even one here. So that's going to be 2 times 165 Hertz so that's gonna be 330 hertz. F3, the third harmonics, is 3 times 165. Okay, it's always the number of harmonics times the fundamental frequency, so that's gonna be 495 hertz. Okay. We can keep on going, but we only want to write down 3 lowest frequency, and this is the answer, right? This one, and this one. All right, now let's change the configuration of the pipe a little bit. Now let's close one end and answer the same question, which is what's the lowest 3 frequencies of standing wave that can fit into this system. But now one end is closed and the other one is open, so you only close one of the pipe. You might ask, like, can we close the 2 ends? Well, you can, but then you cannot really put in sound wave, right? It's kind of hard to do, and so we're not gonna talk about that. So in this case, this is equivalent to the string where one end is free, right? So this is kind of equivalent system. So we can use this system to calculate everything, right? So what's the lowest frequency? The lowest frequency is when the wavelength is longest. So in this case, we have half the lobe, right? Only half of them. So one lobe is lambda over 2, half of them is 1/2. So 1/2 times lambda over 2 equal to the whole length, which is L. So lambda is 4L, and L is 1 meter, so lambda becomes 4 meters in this case. So the frequency is V over lambda. So 330 divided by 4, and you get 82.5 hertz. So it's half of what we had before. And the only thing which is different is you just close one end. Right? You can put your hand to close one end of the pipe, and the frequency suddenly jump to half what we had before. This is F0 for this case. What about the next one? Well, this is the case where you don't have even harmonics. So the next one is the third harmonics. So F3. So it's gonna be 3 times F0, and that's gonna be equal to 247.5 hertz. And the next one, again, we skip all the even harmonics, so it's not 4 times, it's gonna be 5 times because it's 5th harmonics. So that's gonna be 412.5 hertz. Right. So you can see that by simply putting your hand to one end of the pipe, you change the structure of the harmonics of the system entirely differently. Okay, so the frequency of the standing wave are different, totally different. Okay, so how you set up the end condition for the pipe gonna influence how the frequency, how the allowed frequency gonna be in terms of this standing wave. Okay, and one last thing is that, so when some of you might have played like this kind of instruments before, and then you so what you do when you open or close the holes, of a flute or recorder or something, so you effectively change the length of your tube, right? And I mean, a trombone probably the best example, but in terms of flute, you need to open or close the hole to effectively change the length, right? So what's happened is that you're trying to blow at the other end, right? So you're trying to kind of excite randomly any frequency that is trying to excite, but only this one gonna get excited more. So in the end, this is what you're gonna hear, because this is the only frequency that kind of survive and give out nice standing wave. So remember, if you put in the wrong frequency, right, you're still gonna have wave inside the tube, but they're gonna well, by they I mean like the incident and reflected wave gonna interfere kind of randomly, right? So you don't have nice standing wave. So eventually you're not gonna hear much for the wrong frequency too. So the only correct one gonna survive in this case. Okay, so that's why when you look at like an organ in the church, you have like different length of the tube, and that's just for different frequency, which gives you different musical notes. Okay, and then you can play, you know, any sophisticated, you know, piece on this instrument. Okay, that's what I want to say about like this standing wave in string and in air pipe, air column. Next we're gonna talk about light wave, but that's probably after the break. Okay. So you mean this page? Yeah. Is this the one, or is this one? Which one you want to look? Oh, you saw it, right? Okay, good. All right, so let's take a 10-minute break, and then we're gonna come back and talk about light wave, which kind of a little bit different. All right, so I'll see you in 10 minutes.